Hi, my name is Simon Burton and I'm presenting this paper today. I had a lot of fun working with Dan Browne on this result. It all began with a simple idea which took just a few hours to test. I was doing some simulations on a computer, and in about an afternoon I had worked out there was some phenomenon going on. And then it took a couple of months to map out the boundaries and exactly characterize this phenomenon. Okay, let's get into it. So, you want to build a quantum computer. First of all, you're going to have to find a way to protect your quantum information from the big bad world. Somehow put a box around it. But at the same time, we want to leave open the possibility for some manipulation of this quantum information. These two goals stand in opposition to one another. The more you protect the quantum information, the harder it becomes to also be able to manipulate it, and vice versa. There's a lot of results in the literature that characterize how much manipulation is available given how much the quantum state is protected. And the result I'm talking about today is another example of this kind of phenomenon. One of the best ideas for protecting quantum states is to use a stabilizer code. For example, encoding a single qubit into a tensor product of qubits. Then over in the stabilizer code, we measure stabilizers and perform error correction to protect our quantum state. For manipulation of the encoded state, we can look for transversal gates. These are tensor products of single qubit unitary operators such that the resulting operator preserves the encoded space. And transversal gates should be inherently fault tolerant. Each one of these gates can only cause an error on a single qubit, and so if we perform these gates well enough, we end up with uncorrelated errors across the code, which can then be error corrected using the stabilizers of the code. The codes I'm talking about today are the hypergraph product codes, which generalize the surface code. And for the gates, let me just set up some notation here. I'm going to write C0 for the phase group, plus or minus 1, plus or minus I. C1 is the poly group generated by the X and the Z operators. C2 is the Clifford group generated by these matrices. And I guess we're using tensor products as well. The main theorem of the paper goes like this. We're given hypergraph product code, and I'm going to notate this as A tensor B, which I'll explain in a little while, such that some more fine print over here, which I may or may not explain, then transversal gates are restricted to the Clifford group. The ingredients come from an argument by Bravi and Koenig. It relies on this little lemma here. So we're given an arbitrary unitary operator U. U is going to be a Clifford operator if and only if this thing is a phase for all P and Q Pauli operators. I think this is the only bit of algebra I'm going to show. And the idea is we're going to apply this to the encoded subsystem in the code and the corresponding logical operators of the code. So what's going to happen is that the P and the Q here are going to be logical operators of our code, and we have some freedom in choosing those. we need them to apply to all encoded logical operators. So it sounds like we don't have any freedom, but what happens with stabilizer codes is that different physical operators can correspond to the same logical operator. So that's the wiggle room that we have to play with here. We choose different implementations for the P and the Q here. And what this is going to look like is that we're going to demarcate some regions on our code, and this region is where our P operator is going to live, and then this region is where our Q operator is going to live. And if the intersection is correctable, like there's no logical operators living on the intersection here, then this lemma applies, because this encoded commutator has to be a phase. It cannot contain any encoded logical operators. The hypergraph product is built from two classical binary linear codes, which I'm calling A and B. Let me just show you an example for A. This is a repetition code on 5 bits. Over on the right side is the parity check matrix. So this eats up length 5 column vectors and tells you which bits in that column do not agree with their neighbors. And I've also drawn a nice picture of this over on the left. And the 5 bits are these 5 edges. And if I click on an edge here, I can get it to activate it, switch it to 1. And the checks, there's 4 checks. These are living on the vertices of this picture. And I like the picture. It's kind of like an icing model. Each check is just sitting in between the 2 bits that it's checking. And when they don't agree, the check is activated. And when they do agree, the check is 0. So the important thing about codes is these code check matrices, they have a kernel. The code space is the kernel. And in this case, there's one non-zero vector in the kernel, and it's all ones. And I've managed to work it out here just by switching on all the edges in the little icing model. For the code B, it's a little bit weirder. This time there are 3 check operators, and it's weird because there's 3 bits and there's 4 check operators. So it's weird because no matter what you do with the bits, you're going to frustrate some of these check operators. So this code is kind of degenerate. It has no kernel, no code space, but there's a kind of a dual code space or co-kernel. And the idea is that the kernel is the space of vectors that you feed into this matrix, the check matrix, and get 0. The co-kernel is the space of vectors that you check on the other side. I guess it's the output. You take the output of this matrix, and the co-kernel is what kills the output. So the kernel is the inputs that give you 0, and the co-kernel is acting on the other side to give you 0. In this case, there's one non-trivial vector in the co-kernel, and it's this guy. And the reason why is because all the check outputs of this matrix have even weight. And so to kill all these vectors, we just use this co-kernel of all ones. So it's kind of the same answer as the A code. The A code had a kernel of all ones, and the B code has a co-kernel of all ones. And so you may wonder why I'm torturing you like this with kernels and co-kernels, and why didn't I just use kernels all the time? And I could have by transposing this B code, but there's a geometric picture here which I'm going to show you next. The hypergraph product in this example is a surface code. I like this picture because you can really see the geometry. The points in the A code multiply with the points in the B code to give you a point in the surface code. And similarly, a point times an edge gives you a horizontal edge in the surface code. An edge times a point gives you a vertical edge in the surface code. And an edge times an edge gives you a face. This tensor product notation comes from homological algebra, where this really is a tensor product of chain complexes. And let me just play around with some operators on the surface code. If we put a Z operator on an edge, then it's going to frustrate these vertex operators. And an X operator frustrates the face stabilizers. And if we try to make a little loop like that, we get a stabilizer. And if we make loops of Z operators, we get a face stabilizer. And if we try to escape off the edge, we find that we can only escape off, for the Z operators, we can only escape the top and the bottom edges. We can't go left to right. It's the same reason we found with the B code that we couldn't write down anything in the kernel of the B code. We have to use the kernel of the A code to get a logical Z operator. And the logical X operator, how do we do that? Let's see. The logical X operator can escape off the left and the right edges of the surface. Right. But if we try going off the top and the bottom, then we can't escape that way. My friend Mike Vassmer likes to call this the quantum repetition code. So how does the Bravy-Koenig argument work? The idea is that we build a complete set of logical operators that live on this gamma region, this L-shaped region. So let's get to it. This is a logical Z operator, and a logical X operator is a horizontal guy like this. So a complete set of logical operators is supported on this L shape. It's either going to be a Z or an X or both or neither, and it fits there. And then we do the same with the delta region. Let me do this Z operator here and an X operator going along the top. Now we can see the overlap is just the two qubits, the one on the top left and the one on the bottom right. And there's no way to fit a logical operator inside these two qubits. So this overlap region is going to be correctable, and the Bravi-Koenig argument then tells us that transversal gates for this code must be Clifford. How does this argument generalize when we replace A and B with some other classical codes? Let me just show you the general setup of what the logical operators look like. For the surface code, we were putting down these strings of X operators which corresponded to the co-kernel of the B matrix. In general, this co-kernel is going to be bigger than one-dimensional, and so then what happens is every row in the co-kernel needs to be copied onto this horizontal string here. So we get one operator on this string for every row in the co-kernel. For the surface code, there was only one guy, so it's just that. But then we need to copy these string operators and that copying is controlled by the kernel of the A matrix. So for every row in the kernel of the A matrix, we need another copy of the X-like strings here. For the surface code, this KA was just 1, so we didn't need to do this. And there's another thing that's breaking down here, which is that as soon as we copy these X strings in the surface code, we got a stabilizer. So in general, there's 3 ingredients that we need to satisfy. And the first ingredient is that we don't hit a parity check in the A code. So that's easy to do in the surface code because we only have we only hit one edge in the A code, and that's not a parity check. The second ingredient to get this Bravi-Koenig argument to generalize, let me bring up what that looks like again. When we form these intersections, they need to be correctable. And what that amounts to is that when we're creating these strings, we need to avoid the kernel of the A operator. And the kernel over here was this thing. So this is pretty easy to do in the surface code. We only ended up covering just one of these bits with our string, and it did not touch logical a kernel, some guy in the kernel of A. So for the surface code, this was really easy. But that's the second ingredient. We need to put down these string operators, K, A, many of them, and avoid the kernel of A. And the third ingredient is that we need to do this twice, and we need to do it on disjoint sets. So we need 2 disjoint sets on A and 2 disjoint sets on B, so that we can form this intersection. If we manage to pull all of that off, then the intersection will be correctable and the Bravik-Koenig argument goes through. In the paper, I exactly characterize which matrices A and B you can do this for, and it's kind of neat what the answer turns out to be. Thanks for listening.